Part 8 for the General License Upgrade class from the Hearst Amateur Radio Club in October of 2019. Again, the question pool goes from 2019 to 23. This is a long episode, so let's get started.
Shut up and sit down.
Ground. In a lot of places in the country, it's called earth. And in Europe, they like to call it earth, earthing. When we ground stuff, they earth it. And there's a reason. Typically, the importance of ground is a common reference point. It's a point that pretty much everything is measured from. Measure relative to the ground. Schematically or symbolically, you see a symbol like that. And that's typically used to describe an earth ground. Mother Earth. Think of that as looking like maybe a spade that you put in the ground pointed on the end. Artificially ground, something that represents the earth, usually uses that symbol. The common chassis, the metallic chassis on your radio, your transceiver, that everything hooks to, that the negative side of your voltage hooks to. That usually looks like that on a schematic. Ground's good for you, especially if you're going to put an antenna outside. There are any number of ways of getting ground. The best, typically you get ground with a ground rod. Multiple ground rods are better. More is better than two is better than one. Three is better than two. When you hook up to that ground, if you can, especially if you're grounding your station, a flat ribbon is probably your best ground. A flat copper ribbon, copper strap. Barring that, if you don't have that, a good, heavy, solid wire is good. And you want to use a solid metal connection, something that looks like that. That's made to ground onto a pipe or a ground strap. You put that on the ground rod or the ground pipe. You put your wires into there. This one here does the same thing. You slip it on the top. You slip the wire down in here, and you clamp that, force that screw to force the ground rod against that metal connection. 8 foot's is a suggested length for a ground rod if you can get it. I don't want to be this guy. There may be a better way of driving that ground rod, but I don't want to necessarily be that guy. This guy up here on the top swinging a hammer over his head. Yeah, I don't want to be that guy. Hanging over the edge of the stairs. Don't.
So I tried to put a grounding rod in, high clay soil, 8-foot rod.
Mm-hmm.
He ended up dislocating both shoulders.
Yeah. An impact hammer is a good way to do it. Use an impact hammer. There are other devices you can pound down that are good, but impact hammer works well. Goes through clay and goes through rock. Don't solder. Use that mechanical connection that we talked about here. Don't solder. The thousands of volts and thousands of amps that come with a lightning strike will vaporize that solder. It'll be totally ineffective. Typically, a lightning hit is not a single shot. Typically, a lightning hit is multiple strikes up and down. Typically, a lightning strikes, charge goes up from the ground, charge comes down from the clouds, it makes an ionized path, and the strike may go up and down several times. The first time that any high current at high temperature go through that solder connection, it's gone. It's no connection at all. So you make sure you use a mechanical connection. When you talk about soldering, those of you who've done soldering, still, although environmentally lead-free solder is the preferred solder, most hams still use a lead solder. They use a tin-lead combination. Be aware of the fact that if you're using tin lead, use proper precautions. Wash your hands well after any time you solder. Don't go off to lunch after you've handled solder for a long time and contaminate your food with lead. The downside on electronic circuits that they've found with lead-free solder is it tends to grow whiskers. It tends to grow little solder whiskers. It starts looking like fuzz. and they start shorting the circuit out. And you'll see a lot of components will fail because of whiskers on tin lead solder. On lead-free solder. That's why most of us ham still, if we're going to do something, we still use tin lead solder. I still use it. I find that it flows a little better. But you use what you feel good about. Ground's important. If you're going to ground your station, you want to ground your station for several reasons. One of the reasons is for lightning protection. One of the other reasons, in case you find there's an internal short in your radio or internal defect in your radio, it also helps reduce noise. When you want to ground, you want to start out, preferably, this is ideal, use an 8-foot ground rod. Clamp your ground strap securely onto that. Use a strap whenever you can. Use a low impedance conductor. Get that ground rod as close to the house as possible, as close to your station as possible, because it's working on the other half of your radio. Half of your radio is connected to the antenna, the other half of the radio is connected to the ground. And that will become, at certain lengths, it could act like an antenna. So you want to keep that as short as possible. You want to ground everything. Make sure that you're using 3-wire conductors in your house that go to a good internal ground. This ground is external from your house. This is in your wiring here. A good way to do that is make a common point to ground everything to. This suggestion here shows a piece of half-inch copper pipe, and each component is individually tied to that single point ground, which is that ground pipe or ground bar, or even a big copper plate, whatever. Tie those all to a single spot that goes outside to the ground. Electrically, you want to tie them to the ground. What you don't want to do is you don't want to tie to the radio, and then from that radio you go to this radio, from that radio you go to this radio, from that radio you go to this radio, because each time you do that there's a resistance there, internal resistance, and these start going above ground. Now you've got a resistance, you've got a voltage that's above ground, and all of a sudden you may start getting feedback. You may get what's called a ground loop. And so you want to keep these all as close to ground as possible. Don't daisy chain your equipment together. All go to a common point in your operating system. Like I said before, avoid long ground wires that may be resonant in some frequencies. You don't want them to act like an antenna. It'll cause interference, hum, and you can tell if you've got a ground loop because you're going to have hum and distortion in your signal. Yeah?
On my house, half of it's grounded, half of it isn't, and my radio room is the half, or in the half that is, but with the UPS, and this is something I read when I bought my first one, is it true that if you're plugging a UPS, even if you put a 3-prong outlet on your non-grounded side of the house, that's not going to really work, is it, the UPS? Doesn't it have to have a grounded?
You're talking about an uninterruptible power supply.
Right.
I don't know that a UPS necessarily has to have a ground. Yeah.
Okay, all right.
I mean, a ground fault interrupter will even work with a 2-wire system.
Okay.
But UPS aren't normally operate dependent upon the ground.
Okay.
They're looking for the absence of voltage to trip the internal battery and connect the battery to the circuit. But if that part's, you still might want to have a nice outside ground.
Right.
Talk a little bit about interference. A lot of people, you'll be subject to interference at one point or another. You may cause interference, or you may receive interference. You may be subjected to interference. Some of the interference you may see is phone interference. If your radio couples, if your antenna, if your RF energy couples to a telephone line, to a landline particularly, what you're going to get is distorted speech, and that's going to be on the telephones or audio devices. If it's a CW signal, you can hear it by an on-off humming or clicking sound that corresponds in cadence with your CW signal. You can minimize that, especially if it's on stereos and things like that. I had a stereo system that loved to, whenever I talked on 6 meters, it loved to have my signal come out the speaker. And it just so happened that the speaker wires I had were multiple frequency of the antenna length of my 6-meter antenna. I put some bypass capacitors over, just plain old disc capacitors. I put a disc capacitor across the speaker leads, and that solved the problem. Sometimes you can always also use a ferrite choke. A ferrite choke is essentially a piece of conductor like in the center of your transformer. This is wound on this coil here is wound on a ferrite choke. You can put one of those on your wire, loop your wire through it a couple times, and it'll cut down. It'll break the RFs on the signal that's being superimposed on the conductor that goes to the device. So you can minimize that way. Receiver interference. Back in the beginning, when they first started playing with radio, they used a spark gap transmitter. And the spark gap, you can see that here. There's Guglielmo, I think that's Guglielmo Marconi there, and a spark gap transmitter. You could see what it did is it made this big arc, nice big juicy arc. And they switched that arc off and on with Morse code long before voice. That was the first original digital signal. It's Morse code. Turn it off, turn it on in a predetermined pattern. That was just rich in harmonic radio frequencies. Pretty much wiped out a whole band. Harmonics of that was just unbelievable. So you would hear that on several frequencies. Well, back when there were just a few people doing this, nobody cared. Nobody cared at all because you normally weren't interfering with anybody. There was nobody else on there. Maybe 3 or 4 people on the airwaves, so that's all they worried about. As time went on, we refined that and didn't use spark gap anymore because of the interference. However, you talk about a spark gap, you're going to see some of that sparks sometimes in power lines that don't have good connections. Bad connections on your power line. And you're going to get sparks. There's going to be arcing. And that arcing is just like this spark gap. And it produces radio interference rich in harmonics. So that's going to be a received signal. You can usually find that out. One of our guys here, one of our VEs, I went over to his house one day and he said, I've got this horrible noise in my radio. He said, I can kind of get it out with the noise blanker, but he said, I've got horrible noise. So I tuned to the frequency he was on. I stood in the middle of his backyard and I heard some interference. And I walked to his front yard, and as I approached the power lines, it got louder and louder and louder and louder. I said, Jack, I think you got interference coming off your power lines. And I walked to the power lines in the backyard, and it got louder and louder and louder and louder. He was sitting between 2 power lines, both that had some sort of arcing interference. He goes, it started just right after I saw the power guys up on the poles down at the end of the street. He said they seemed to be doing some work down there. Whatever they did, they didn't do a good job of it. That interference, you can only get rid of that by having your power company do that. Your power company has to take it. Pardon?
Will they come back out if you tell them that?
Oh, he had a big fight with them.
Yeah.
No, not us. And he had to do the same thing. We had to go to the radio and say, okay, your power line gets louder. Your power line gets louder. Why is your power line interfering? Now, what's this ham radio now? Why is your power line interfering with my shortwave radio so I can't hear shortwave broadcast of music? Then they were interested. They weren't interested he was interfering with ham radio transmission. They were interested, well, once you start saying, I'm either interfering with my music radio or interfering with commercial radio, they'll be right out there. Now, they're not always that. Sometimes they're more sympathetic than that. A lot depends on who you've got, who the technician is, whether he understands, who takes the call on the telephone, and how much you can impress them, what you know. Gain and loss. Gain. We typically talk about gain. Sometimes an antenna system is a good place to talk about gain. Gain is usually expressed as a ratio between something and something else. Based on something, how much something increases or how much something decreases is called gain, especially a radio signal. It can be a positive gain or a negative gain. Typically we use decibels. Decibels to describe gain. Decibels describe a ratio between one power level and another when we're talking about power. Or loss. One power level and another. Decibels are not linear, they're logarithmic. Why would we use something so esoteric as decibels? Well, the good thing about that is you can add and subtract them directly. And get a reason, you could add gain. Essentially, you're adding a ratio and adding another ratio, or adding another ratio to subtracting another ratio. It makes the math a lot simpler. But the way it works is that the multiplication factor, if the thing you're comparing it to, the two things you're comparing are the same, the gain is 0. Nothing gained, no gain. If what you're comparing it to is twice as much as what you compared it to, the gain is 3 decibels. If it's 4 times as much, it's 6 decibels. If it's 10 times as much, it's 10 decibels. 100 times as much is 20 decibels. 1,000 times as much is 30 decibels. It works for both. Here's the math. Power 1, power 2. This is the things you're comparing. When the ratio between these decibel is 10 times the logarithm of whatever that number is. You can figure it on your calculator. But typically we won't have to because we usually talk about generalities. As long as you can remember twice as much power is 3 decibels, 4 times as much power is 6 decibels, 10 times as much is 10 decibels, 100 times as much is 20 decibels. You can kind of guesstimate in the middle. You can see those are not uniform. 3, 6, 10, 20. You can see they're not uniform, they're logarithmic. They're not analog, they're logarithmic. So doubling the effective power is a 3 decibel gain. Cutting the power in half, dividing by 2, is a 3 dB loss. So it could be a positive or a negative. How we would use that, we're going to talk about coaxial cables later. They have a loss. They have a negative decibel. So based on their length, they have a negative decibel. We're going to talk about antennas. Some antennas have a positive decibel gain, or some antennas have a decibel loss. You can take your power, you can figure out your power on your radio. If I got 5 watts and my coax dissipates 3 decibels worth of power, I've only got half as much power at the end of the coax. But then if I got a 3 dB antenna, I gain the effective radiation back again because I added plus 3 and minus 3. Dipole antenna, most common form of an antenna. It's kind of the standard. It's a half wavelength long. A typical doublet dipole is a half wavelength long. Let's see if they left me a dipole here. This is a dipole antenna. I'm going to ask for a volunteer. That's a dipole antenna. Real live dipole antenna. There's where I hook my feed line. This is where I put the RF energy into it. And that spot right there. 1/2 connects to here of the coaxial cable. The other half connects over there. How long does that look like it is? How long do you think that is? Pardon?
6 feet?
Yeah, could be. If that's 6 feet long, what band antenna do you think that is? How many meters? It's half of a wavelength. So the wavelength I'm measuring is twice that long. That wavelength would be, if that's 6 feet long, the wavelength I'd be measuring would be 12 foot. It'd be a 12-foot wave. That's half a 12-foot wave. I think it's probably a little longer. Maybe that's about 9 feet. I think that's 9 feet. That's a 6-meter antenna. So that would essentially be 3 meters long. 3 meters is about 9 feet. And that would, at 9 feet, right on frequency, my impedance would be 50 ohms right here, or just about 50 ohms. Thank you. That's a dipole. This is the standard. This is the antenna essentially, pretty much you compare, practically, you compare other antennas to. There's one thing known as an isotropic antenna. That's a theoretical antenna. It's a single point in space that in a vacuum. It radiates equally all the way around. It doesn't really exist. Practically, the dipole antenna is the thing that's the standard, though. The dipole is your next standard. Feed point's in the center. Optimum height is a quarter wavelength above the ground. Optimum length is a half wavelength long on the frequency you want to operate on. The distance above the ground influences a couple things. The distance above the ground influences the feed point impedance, what the feed point impedance is, and it also influences the radiation pattern. As the distance to the ground decreases, what would have been essentially a 50 ohm antenna, as that decreases, that feed point impedance decreases. There's an antenna we like to use known as the NVIS, Near Vertical Incident Skywave Antenna. Remember back when we talked about the maximum angle that you could transmit before it went through the ionosphere? That critical angle, when we talked about propagation? And that's what, if you shot this radio wave up at a high angle and it didn't go through, it'd bounce back down close to you. Well, if you want to talk to somebody close, like from Texas to Oklahoma, you might want to use that short propagation path rather than the long propagation path, which they'd be in the skip zone then. So now we're learning how to direct our antenna. We're learning how to direct that radiation pattern, that path that the RF signal goes into the ionosphere. We can bring that antenna down low, 1/10 of a quarter wavelength above the ground. 75, 80 meters, 40 meters, it's going to cause the radiation pattern to be almost vertical. Not long distance, but short distance. High radiation pattern, near vertical radiation pattern, it's going to give you a short hop, which if that's what you want, that's great. If you're doing emergency for communications, for example, they used a lot of these antennas, a dipole antenna, they'll put up an NVIS antenna, for example, in Katrina, where all the infrastructure was out, the computers were out, the internet was out, they wanted to communicate, but they wanted to communicate just outside of their area because they had equipment staged. All relief agencies had equipment staged a state or two away. They moved that stuff in far enough away to be out of the path of the hurricane, ready for that hurricane when it came in, but they didn't want, when they transmitted, they didn't want to skip over the top of them. So they put down an antenna low to the ground, and they'd use NVIS to bounce that thing for the short path. The problem is that now you got a radio that expects about 50 ohms, and you don't have 50 ohms anymore. One of the things you can do with that antenna is that don't put the feed point right in the middle. You can shift that feed point off center. You can shift the feed point around. Whoa! You can shift that feed point off center and cause the radiation, since the impedance is going down as the antenna goes down, you can shift it off center to cause your feed point to increase. So on a dipole, if you move that feed point off the center line in either direction, it increases the impedance of the antenna increases. So you can move that feed point off center to compensate. And typically what you'll see, that's what they do on an NVIS antenna. It's a dipole close to the ground. On a dipole, now we're looking down at the top of the dipole now. This is a bird's eye view. A dipole antenna is going to radiate at right angles, or broadside to the antenna. You're going to get not much radiation off the ends. The direction of maximum radiation is going to be broadside to that antenna. So if this is my dipole antenna, my radiation is going to be going this way and this way, or that way and this way. Not much this way and not much that way.
What about interference like a building or a house or?
Well, depending on the frequency, sometimes it doesn't make any difference. Sometimes it will affect the radiation pattern. Some may reflect back. It may even distort the radiation pattern a little bit. If you've got it close to your gutters, it may distort your radiation pattern a little bit. It just depends where it's at. Some buildings, if you got the neighbors' houses, might not make a bit of difference. but their gutters might.
So you would have to test it with an analyzer to really tell, right?
You want to test it with a field strength meter, yeah. You want to go down or get just a cheap relative field strength meter and go one way up the neighborhood, see your field strength, go the other way, see the field strength, and compare the two of them to see if they're equal. Unless you want to invest a lot of money in a calibrated one, which may or may not serve your purpose, just knowing relative how much it is, one direction or another makes a difference. This is good for us because we're going to talk about directional antennas in which we can now start using more elements in that antenna to force the radiation pattern more in one direction than less in the other. One of the things we talk about is trap dipole. Now this one here, go back. This dipole, the typical dipole, is good for one frequency. And it will work on exact multiples of that frequency as well, but the feed point impedance is going to be way off. So when you use the formula to calculate the length of a half-wave antenna for the desired frequency, if you go up twice that frequency, yeah, it's going to radiate, but the feed point impedance may be 500 or 600 ohms versus the 50 ohms that you want. So how can we fix that? Well, we can fix it by changing the length. We can change the length to a quarter wavelength of the other frequency we want, but then we can't use it for the original frequency, unless we use something called traps. Traps is like a filter. I've got an antenna here, and this is cut for 10 meters in length. This is cut the length I need for 10 meters. Okay. I have traps here that at any frequency below 10 meters, it poses a high impedance. It resists the flow of current, of RF current. So it blocks RF current. It traps we call them traps because essentially it traps the RF current and doesn't let it go past the length that's the right length for 10 meters. At 15 meters, this is 15 meters length here. This is the length I need for 15 meters. This trap out here is still the inactive section. It still traps it and doesn't let the RF energy go past it. But it does let this one here, the 15 meter trap now, has a low impedance at 15 meters. So it allows the antenna now, the RF current, to see this entire length. And by the time we get up here to 20 meters, both of these become active. Then that particular one is sized electrically, so it allows you to see the entire antenna. So you can have one antenna with different traps, and you can have get three good impedance on 3 different bands. There's a disadvantage. Really bad harmonic rejection. Remember, harmonics are exact multiples of the original frequency. And harmonics are not often what you want, unless you're building something specifically for harmonics. If you're transmitting on 10 meters, you don't want to also transmit on 15 meters and 20 meters. So these have poor harmonic rejection because if your transmitter's not clean and it's transmitting harmonics, and when you transmit on 10 meters, it's also transmitting a second harmonic on 20 meters, or 20 meters transmitting on 10 meters, you're going to get that radiation. It'll allow it to go through. It doesn't know the difference. It doesn't know a harmonic from a primary frequency. That's the difference. But the traps automatically change the RF length, with the radio frequency length of an antenna based on frequency. That make sense?
How do those harmonics sound when you're transmitting?
Sound pretty much like the original signal.
Really?
Yeah. You've seen them. Anybody got a dual band antenna? A dual band radio? It's a dual band radio. There's a trap in there. This antenna will transmit on 2 different frequencies. It's good for 2 meters, it's good for 70 centimeters. Let's talk about directional antenna. Directional antenna typically starts out with a dipole. The one we're going to talk about is a dipole, and 1 or more passive elements. This dipole here is a half wavelength long, electrically a half wavelength long. That's called my driven element. That's the one I'm putting RF energy into. And I have another one that's a little bit shorter. That's called a director. Now that pattern I had where I had equal lobes on one side and the other. I had equal power going this way to going that way. I don't have that anymore. I've got more power going in the direction of the radiator. Of the director. I've got more power going in the direction of the director. And I've got less power coming out this way. Because now this is influenced. Like we talk about stuff influencing, this influences this dipole, distorts its radiation pattern in the direction, a good way, in the direction that I want. I can make it even better or different. I can also do the same thing by putting a slightly longer section behind this, what I call on the backside, and it will call, it's called a reflector, and it will distort that pattern as well and reflect the energy from the driven element in the opposite direction of the reflector. Both of those do the same thing. That's great. The question is, can I get better? Sure. I can put all of them together. I can put the reflector at the right distance, I can put the director at the right distance, and I get a lot more radiation going this way than I get in the back ways. It's called forward radiation. On this one here, forward radiation gain on a 3-element dipole are called a Yagi. This is called a Yagi. The guy that developed this was a Japanese guy. His name was Yagi. It uses, I get 9.7 dB gain, isotropic gain, dB gain relative to just a pure dipole. So now I've got almost 9 times much power that I would get in this direction on a dipole antenna, now going this way versus that way. That's the front of the beam. Make sense now? I'm influencing this thing and I'm not gaining any overall power. It didn't take 5 watts and make them 10, but it took 5 watts and made it sound like 10 watts or more. Oh, 10 times, like 100 watts. Pardon?
Is it transmitting anything behind the
A little bit. Not much. Not much behind it, not much off on the sides. This is called the back, the direction that I don't want, the direction I'm not pointing in is called the backside. The direction I'm pointing to that I want, that I'm interested in, that's called the front side. Make sense? Front and back. Front and back, well, it's the front and back ratio. I can put even more. I can keep putting more directors and more directors and more directors on there, and I keep taking what I'm doing with my radiation pattern is I'm taking that figure 8 shape pattern that I had in the dipole, I'm taking that thing, I'm smashing it down, and I'm bringing it in and forcing it into a narrower and narrower beam. It's like focusing with a beam, with a light beam. It's like taking a wide light beam. You know, you all got those LED lights that you can move the thing in and out, and you can take the beam from wide to narrow. That's exactly what this thing is doing to the RF energy. It's changing the number of elements, changing the spacing of the elements, and changing the length of the boom. These are all going to be mounted on a boom, on some sort of support. Change the length of the boom. I can optimize my forward gain of my antenna. My forward gain is the main lobe. This is that antenna. This is what that lobe's going to start looking like now. Here's, as far as the effective power, the power that I'm putting out. I'm putting most of this power this way and just a little bit of the power this way. This is the front lobe. It's called a lobe. That's the back lobe. And the more elements I put on this, the narrower this thing gets this way and the farther it goes out that way. So the front to back, the antenna gain is a directional advantage it has compared to a dipole. And the radiation from the back of the antenna is the rear lobe, and the radiation from the front of the antenna is the front lobe, and the front to back ratio is the forward front dB, gain in dB, versus the minus gain in dB. I never got, still, if I had to start out with 5 watts, it's still 5 watts. I don't get any more power, but I get it more effectively. Instead of scattering it all over in a big circle, I'm pushing it all this way, and very little of it behind me. It's called effective radiated power. Effectively, now if that's 10 times as much there, that's 10, let's say that's 10 dB, I'm getting the equivalent of my 5 watts of 100 times more talk power than I would have gotten from just a dipole. Because remember, 10 dB is 100 times gain. I'm sorry. Right. I'm getting a lot more power going on here. Make sense, that? That's the advantage.
How wide is the spread, though?
Depends on how many elements you have in the design of the antenna. Most antennas will have, antenna designs will have a pattern that you can look at where they've they've analyzed it, and it'll show what the radiation pattern of the antenna looks like. That spread is dependent upon the gain of the antenna. The more gain you have, the narrower the spread. The less gain you have, the wider the spread. Because in that narrow spread, the gain's a lot less over here than it is right here. Effectively, if I'm standing over here, I hear, and I move over to here, my signal sounds a lot louder. A log periodic antenna, that's kind of a cool antenna. That antenna uses a logarithmic calculation to determine the spacing between the antenna elements and the length of the antenna elements. You feed it on the front, maximum gains that way. The advantage of a log periodic antenna is it has a very wide band spread on it, bandwidth. It's got a wide bandwidth. Sometimes, some log periodic antennas you can use a single antenna. Now the Yagi we showed you without traps is a single band antenna. Okay? This can be a multiple band antenna. Cushcraft used to make an antenna that used to do 6 meters, 2 meters, and 70 centimeters, all in one antenna, based on the design, the logarithmic design of the spacing and the length of the antennas. It's also a gain antenna, a directional antenna. There's a quad antenna. Quad antenna works somewhat like a dipole antenna. It uses a full wavelength loop, about a half wavelength on either side, quarter wavelength on either side, and a reflector behind it, about a quarter wavelength bigger than a full wavelength. It's on a boom. Those are two connected. There's a support on a boom. Forward gain is about the same as a 3-element Yagi. But where a Yagi would be a half wavelength wide, this thing's a quarter wavelength wide, so it takes up more real estate horizontally, although you add more real estate vertically. You can also make it if you move the feed point from the bottom, it becomes vertically polarized. The feed links on the bottom becomes horizontally polarized. Also a delta loop antenna. Delta loop antenna is also a full wavelength all the way around. It's about a third wavelength on each side, 3 sides, divide it in 3. Feed it down there, it's horizontally polarized. It's about a quarter wavelength apart. It's approximately the same gain as a 2-element quad. So it's about the same gain as the quad, which is, we said, was about the same as a 3-element Yagi. So it's the same as a 3-element Yagi. And there's a receiving antenna that people like to use, and this is a directional receiving antenna. It's called a beverage antenna. It's 1 to 4 wavelengths long. So on 20 meters, let's say 80 meters. What's the minimum size that would be on 80 meters? How long would that be? It would be 80 meters long. About 250 feet, up to thousands of feet. The feed point is on one end. It's got a terminating resistor on the other end. It's adjustable, about 1,000 to 2,000 ohms. It receives best from the feed point end. This end. Primarily uses a receiving antenna on the HF low bands. On the very low bands, it's about 3/10 to 4 meters above the ground. It has high losses. It receives well. It's very directional, but the losses are too high for a transmitting antenna. But it's a popular receiving antenna called a beverage. We talked about a field strength meter. Field strength meter is a device that measures the intensity of an RF energy field in its presence. It's used for antenna and transmitter adjustments, antenna radiation patterns. Like we were talking about, how do you know whether the buildings in your neighborhood influence it? No. Well, you'd use a field strength meter. You'd walk down 3 or 4 blocks and take a reading, and go to the other side and walk down 3 or 4 blocks and take a reading and see if they're the same. If they're the same, the radiation patterns, even if they're not, the radiation pattern's offset. You can use it for radio direction finding. You can use it to find a particular transmitter. If you want to find, say somebody's got with a directional antenna, say somebody sticks the mic down between the seat and the console of their car, and their radio starts transmitting and locks up the computer until the radio times out. And when the radio comes back, it locks it out again. It locks out again, repeatedly, repeatedly, until either their radio burns up, or somebody finds it, or they go out and pull the mic back out. Sometimes they don't know. They may just park someplace. Well, it's a way you can use a field strength meter with a directional antenna to go find them. You can listen on the same frequency they're on, and wherever the strongest is in that direction, you start heading that way. Radio for radio direction finding. RF exposure evaluation. If it's a high dollar, accurately calibrated, that tells you the amount of exposure you have, you can use it to develop a chart to determine whether or not you've got too much exposure at a given frequency. Remember from your technician test, you're supposed to be able to analyze your frequency to see whether or not your exposure is at hazardous levels. You can have a high dollar one, or you can have a simple $15, $20 one. I have one of those. It's not calibrated. I have one of these that I use a lot. It just shows me whether I've got radiation or not. A lot of times you want to know, is my radio actually transmitting? Nobody talks to me. Nobody comes back. Well, I can put a field strength meter right there, click my mic button. If the meter goes up, I know I'm transmitting. I know I've got power. Got a field strength meter. It measures the intensity of the RF field around you. Yep.
What kind of range do those get? Do they have external connectors for different antennas?
Yeah,
or?
some of them do. This is a pretty much simple one. It's used for short range. These can have antenna connections. It depends on the sensitivity of the meter. Whether this one is not amplified, this one is amplified, this one is measured by frequency, this measures, the cheap one just measures RF exposure in general. It really depends, and it depends on the power level, and it depends on the efficiency of the antenna, transmitting antenna. Some of those you can go out several miles. These here, several feet. Vertical antennas. We talked about a dipole antenna, which has two halves, two matched halves. Each was a half. The total antenna is a half wavelength long. Most of your vertical antennas will probably be about a quarter wavelength, because the other half of the antenna, the radiating part of the antenna, is vertical. This is my pointer that I've been using is part of a vertical antenna. And the ground makes up the other half of the antenna, makes up the other half of that dipole. Because on your dipole, when you put a connector on it, one side of the connector is already connected to ground, and the other side is connected to RF energy. So I've got the side that I usually connect to ground that goes back down through my coax cable or my feed line back to my radio. I'm going to use the ground below it. Sometimes we'll string radials out to improve it, depending on how good the ground is. Seawater, really conductive ground, drive a stake in the ground is about all you need. Most earth, especially Texas earth, you need to put some radials down to help couple to the ground. Ground reflection losses affect the feed point impedance. The feed point impedance may change depending on how good a ground you got, but that's a ground-mounted vertical. This one here goes straight on the ground. One of the precautions, if you put a ground-mounted vertical up, they work pretty well. They have a nice low angle of radiation. They're good antennas. But you need to make sure that it's protected so somebody can't walk up while you're talking and grab a hold of the antenna, because they will get an RF burn. I remember when I was a kid, police car had a big 102-inch, or pretty close to that, probably 80-inch whip on the back. And I was talking to the police officer, said, "What happens if I hold on to the antenna when you press it?" He goes, "Don't do that." I said, "What happens if I do?" He said, "Don't do that." I said, "Yeah, but if I hold on," he goes, "Okay." And he keyed the mic up. I heard that dynamotor wind up in the trunk. It was that old, and yow, man, it burned. It's electrical shock, not the one that's going to cause you to grab on and not let go, but it burned. It got RF burn. says, I told you.
Did you?
He said, I told you don't do that. You could also mount one. A popular one is to mount these antennas on the top of a pole, maybe 20, 30 feet in the ground. Higher the better sometimes. And they use these radios on the bottom. There's the other half of your dipole antenna. Each one of these are cut. If you notice on this, you can see this thing here. This thing has traps in it. Remember the traps we talked about? Okay, this vertical antenna has traps in it. So it will be different lengths electrically for RF on different frequencies. And it has radials that make up the other half of the antenna, and they're different RF lengths as well. Vertical antennas. We'll look at vertical antennas versus the radial. I'm going to have to heavy up this lines, but if I have a ground plane, a vertical antenna, and I have my ground plane radials at 90 degrees to them, my feed point impedance is approximately 35 ohms. I really would like to have 50 ohms if I can. So what I do is I droop my radials down about 45 degrees. And by drooping those radials down about 45 degrees, that raises that feed point impedance to 50 ohms. My antenna, my radio likes that a lot better. Even though that's still a quarter of wavelength long, without changing the length, by lowering the radials down, I can bring the feed point impedance up to about 50 ohms. If I pull it all the way down like this, and essentially put a dipole on the end and feed it in the middle, I've got about 72 ohms in there. So the droop of the antenna affects the feed point impedance as well. Vertical antennas. Vertical mobile antennas. Okay. If you're going to be on 20 meters, you want to talk on 20 meters, you want a vertical antenna. A vertical antenna is a quarter wavelength. Approximately, how long does that antenna need to be? What's a quarter of 20? 5 meters. How long is 5 meters? 5 meters is about 16, 17 feet, right? A meter's a little more than a yard. So are you going to run around with an antenna on top of your car 16 feet long? Okay. A lot of overpasses are only 14 foot, 8 foot clearance minimum. When you go into the gas station, if they've got any fluorescent lights under that canopy in the gas station, you're going to knock those things out. I did that one time years ago with a CB antenna, 102 inches long. Pulled into a drive-up when they first opened. I'll show you how old I am. When they first opened drive-ups, pulled in the drive-up, and they had this. Their characteristic of that restaurant was a bunch of fast food. It was a bunch of yellow fluorescent tubes all the way around, and they had yellow fluorescent tubes under their drive-up thing. And I pulled up, and got to the window, was right on the end there, and paid for my meal, and I started down the line. I heard this pop, pop. I speeded up, pop, 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 and I noticed the lights going out behind me. Well, my antenna had bent back enough that once I cleared the drive-through window, it snapped up and hit the first bulb, and then snapped up and hit the second one, the third one, and the fourth one, because it was still going like this as I went down through there. And I took all the bulbs out. So yeah, you can use 20 meters in your car, but that's 40 meters. So, well, how do I do a mobile antenna? And you said maybe it should be at least 5 meters long. Let me show you something. This is a 20-meter MIDI ham stick. There's a magnet mount on the bottom. That's a 20-meter antenna. Does that look like it's 5 meters long? Looks more like 32 inches. Well, how did I do that? Well, 8 foot's about the maximum practical length. You're going to have some kind of loading coils and capacitors to compensate if you have a shorter antenna. If you look closely at this antenna, and I'll take this off of here and pass it around. If you look closely at this antenna, you'll see underneath this heat shrink tubing is I have a coil of wire going around here. And then all of a sudden I have this thing here, which is a really tight wound coil of wire, and I have some more wire going up here until I finally go to the radiating element on the end. Okay? MFJ makes that. It's a knockoff of the ham stick people. That's a shortened antenna. That's a coil of wire. Now, the simple way to think about it is that I've got as much wire in that antenna as I would if I had it stretched out long. It might be somewhere close to a quarter wavelength long. I just coiled it up. That's a simple way of thinking about that. I can make that thing longer. I can make the short antenna longer by coiling up some extra wire. In actuality, it did both. It did two of those things. The really loose loops you see around there is extra wire to make the antenna longer. That really tight one in the middle is an inductor. A short antenna is capacitive. It tends to have a capacitive effect. You offset the capacitive effect by putting an inductor in there. Inductors and capacitors work together, so I essentially neutralize my capacitance by putting a proper inductor in that antenna. Now, is that as good as a quarter wavelength 20 meter antenna? No, no, no. No, it's not. That's called a compromise antenna. There's inductive loading on that to compensate for that. It has a very low radiation efficiency. It is not an efficient antenna. And it's going to interact with the body on my car. If I have a pickup truck and I put that on the bed, it's going to interact with the cab on the truck. It's going to distort the waveform. And that also means I may have to make a different adjustment in the length because it may try to couple. It's going to have a very narrow bandwidth. I can't go very far off the sweet spot before the standing wave ratio, before the impedance of that antenna starts going up. Can't go very far below that, and the impedance goes back up again. So I've got a very narrow bandwidth that I can operate in. The shorter the antenna, the narrower the bandwidth. It's called a compromise antenna. They're a compromise. Doesn't mean there's anything wrong. If that's the best you can do, that's the best you can do. It's best. It's the best you can do for the situation. That antenna, as a compromise, surprised me. I put it on that mag mount on top of my van. I tuned it for a sweet spot in the middle of the general portion of the 20 meter band. And I found out once I got outside of that, but my impedance went up. My radio didn't like it. But I had an antenna tuner that took care of that. And I got out on the road, and I was going on a road trip. I was going to be by myself. I was going to know I was going to get bored. I got out in the middle of Kansas. I got bored. I turned the radio on. I heard a contest on the radio, an IARU international contest. And I heard people talking, and they're all complaining about how bad the bands were, how propagation was horrible. And I heard them, they're pretty loud, so I thought, 100 watts from my radio, I'm probably getting 5 watts out of that antenna. The effective radiation power is probably 5 watts because the loss is so big. I punched the button, I gave them a call sign, they came right back, said, you're 5.9 in Maine. This is Kansas to Maine with a really bad antenna. Okay, thank you. I gave them my signal report and told them where I was at. I thought, well, I hear another guy, tune up down the band, I hear another guy. And I heard some real weak signals in there, but I didn't talk to them. I knew I couldn't, I wasn't a chance. Heard another guy, I thought that was a fluke. Called him, he came right back again. 5.9, Washington State. So I thought I got to start logging these guys. So I logged 27 good solid contacts in about an hour and a half. Only people I heard. Washington, the distances, they were all over the country. The longest distance was Maine, Washington State, a couple in Southern California, a few in Texas, California, southern part of Florida, Mexico, Venezuela, and Puerto Rico, and Cuba. All off that really bad antenna. Now surely, no, I didn't do anything, nothing magic I did. It was just resonant on the frequency. It did radiate. It was the best I could do under the given conditions, so it was the best antenna to use. As anything higher than that was going to get knocked off and tipped over at 70 miles an hour with this mag mount antenna. But it just goes to show you that it's not optimal. Had I had a better antenna, I probably could have talked to a lot more people. But it does radiate. So it's don't forget.
Propagation that night or day?
Propagation was horrible.
Oh,
It was even horrible. Yeah.
Even where you were, it was horrible.
It was horrible. I mean, yeah, and if it had been better, I probably could have talked to more people too. But what I'm saying is that most mobile antennas are going to be a compromise. 10 meters, 6 meters, you can have a full-size antenna. That's not a problem. But other than that, it's going to be a compromise. But don't get afraid of a compromise. But remember, shortening up antenna, regardless of what all the figures say and the advertisements say, there's no such thing as a free lunch. You've got to give something up. You've got to give up bandwidth. You've got to give up effective radiated power. You've got to give something up to get something else. Get that short antenna, I gave up my radiated power, and I gave up my bandwidth. But it still worked. Some of the components of a mobile antenna, a loading coil. That one's got that loading coil wrapped in the middle of it. It cancels that capacitive reactance of the physically short antenna. It makes the antenna look longer. Capacity hat. That also, a piece that sits up on the top. It adds some capacity back to it. It electrically lengthens the physically short antenna. And a corona ball, a little knob on the top, that reduces high voltage discharges from the tip of the antenna. With a sharp point antenna, you'll get some corona discharge off. Sometimes when you talk it, you'll see it glow at night. Those are some of the components of the antenna. The mast, the loading coil, the loading coil, this right here, this section of the antenna is isolated. So that you see this much of the antenna on the bottom, then you see the coil, then it sees the top of the antenna electrically. The inside of that loading coil is insulated. Now let's talk about antennas at your house. How big of an antenna can you put up at the house? Now that you got your general, now you can do 1,500 watts. Now you can talk all over the world. Now you want a tower. What's the biggest antenna you can put up? When you're not near a public use airport and without approval from the FAA, our FAA notification and FCC registration, the tallest antenna you can put up is 200 feet above ground level, or 200 foot AGL. If you're close to an airport, depending on the airport you're at, depending on where you're at from the airport, you may not be able to put up that high of an antenna. You can put up a higher antenna, but now you've got to get the FAA involved and you've got to get the FCC involved to allow you to give you a permit to put up a taller antenna, and it's going to require beacon lights and painted red and white and all sorts of stuff. Now, that doesn't mean just because you're allowed to put 200 foot up antenna that your HOA is going to like it. Your HOA may not allow you to do that. And they're still allowed. You signed to a contract with the HOA. You said, I won't put an antenna up. I understand that. And that's legally binding. There's also local regulations that, as far as your cities. Your city or county may say, no, not in my city you're not going to put out. In a neighborhood you're not going to put up over 30 or 35 feet. That's all. And you require a permit. That's all they're going to let you put up. But when nobody else stopped you, 200 foot above ground level is the largest antenna you can put up. Even with local regulations, they're required by the federal government to provide you with reasonable accommodation for your antennas. HOAs aren't required at this point to provide reasonable accommodations, but local communities and counties are required to provide reasonable accommodations. And the reasonable accommodations are whatever they think is reasonable, and you may have to deal with them legally, or you may have to deal with them on a formal basis without a lawyer, but 200 feet is the answer for how big the biggest antenna you can have when nothing else prohibits you from doing that. That's found, if you want to find out more about a bigger antenna or where you are with regards to an airport, how big an antenna you can have, you can look at FCC Rules Part 17. FCC rules has rules for everything, and Part 17 covers that, and it'll give you a whole bunch of really complicated information on how to tell if you're near an airport how big your antenna can be and where it's at. Review. Grounding's important. The most important thing about grounding is do your grounding outside and try to keep lightning out of your station. It's the most important part. If you're going to use a ground strap, use a flat strap. That's the best one. If you got ground inside your station when you ground your equipment, ground it to a common point, a single point. Because if you risk ground loops, which is going to cause hum and distortion in your transmitted signal. Decibels, those are the things that express the difference between two values. And they're logarithmics. 3 decibels is twice as much. 6 decibels is 4 times as much. 10 decibels, 10 times as much, and I told you before it was 100, it's not on the antenna. 10 decibels is 10 times as much. 20 decibels is 100 times as much. Or a half, a quarter, a tenth, or a 1/100th if those are negative relationships. Some uses for decibels are expressing directional gain of the antenna. We saw that on the front to back ratio. We saw 9 or 10 dB on the front versus a couple on the back. Directional gain, front to back ratio of the antenna, coaxial cable loss, we're going to talk about that in a little bit, and received signal strength. We talked about that, we talked about the S meter. Remember we talked about S meter goes up to 9 and then it goes like to 10 dB over 9 and 20 dB over 9, also on received signal strength. Dipole is a standard reference antenna. It's a half wavelength long. Its radiation pattern is a figure 8 at right angles or broadside to the antenna's length. Optimal height is a quarter wavelength above ground. You lower it down, the feed point impedance increases. If you elevate the center and lower the ends, it's called an inverted V. That dipole antenna with a high center and low ends is called an inverted V. Well, traps give multiple band operation at the expense of harmonic rejection. NVS dipole antenna is a quarter wavelength, a tenth to a quarter of a wavelength above the ground. And the radiation lobe of that NVS antenna is nearly vertical. A directional antenna, or beam antenna they call it, a beam antenna because it's going to act like a light beam. Similar to a light beam as far as focusing it with directors and reflectors. Have two or more elements and focus the majority RF, the radio frequency radiation, in a given direction, a desired direction. Examples are the Yagi. We looked at the Yagi, we looked at the quad. That's the one that has a square. We look at the delta, it looks like the triangle. And we looked at the log periodic. Gain is a direction advantage versus a dipole. How much a given antenna has over a dipole is gain, is effective, a practical gain. Reflector elements are about 5% larger than the driven element, and the directors are about 5% shorter. We can optimize that Yagi antenna that we looked at by changing the number of elements, the spacing between elements, or the boom length, how long the boom is that it mounts on. Mobile antennas are a compromise because they're short in length. 8 foot's about the maximum. There's a version of that antenna, wherever it's at, that short antenna. The standard version of this antenna, this design is known as a hamstick. Was originally developed by a company, and they called their antenna hamstick. This is a shortened version of it. The regular version is about 8 feet long. Kind of follows that 8-foot rule. Not because there's any magic other than 8 foot's about the longest practical length that you can put on a vehicle without beating stuff to death. They have low rate, they require coils or capacitors to compensate for that short length. They have a low radiation efficiency, a narrow bandwidth, and they also tend to interact with the automobile body. Time for a break unless you have any questions.